I'm now recording. So I'm going back to the screen. So what I want you to do is to look at the screen and decide whether you might be able to do these or not. Okay. I'm going to tell you that the electrode potential, the redox potential for zinc is minus or negative 0.76. And the one for copper is positive 0.34. If they do not mean anything to you, do not worry, because I will show you them in just a minute. So zinc is negative 0.76 and copper 0.34. Have a look at those just for a minute and decide whether you can do them or not, because it's important that we do not, that I don't teach you a load of things that you already know. Okay, so just have a bit of a look. I'll give you just 3 or 4 minutes just to have a look and see whether you can answer those. And then I will come back and I will ask you about them. Okay, 1 more minute. So I don't want you necessarily to write down all the question or your answers, just to discuss whether you think you can do it or not. Okay, I'm stopping sharing now. Okay. So number 1 was identify the anode and the cathode. How many people think they can't identify, find the anode and the cathode? Who can find, can't find? Glory, hello. Can find, can't find. Anode, cathode. Can find, can't find. Okay, all right. How many people can write the half reactions? Can write what is happening in the what's it? Some people in Dandura, yes. Some people no. Oshirika, no. Shama, yes or no. Half reactions, not really. Glory, yes or no. Writing equation. Dandura, not happy. Glory, very clever, having a good day. Wamwini have disappeared. And the headmistress says, of course she can do it. She just doesn't want to. If I tell you what is happening in terms of electrode potentials, that's redox potentials. I said zinc was negative 0.76, copper was positive 0.34. Can you work out which one will be oxidized and which one will be reduced? Can you work out from electrode potentials, from redox potentials? Shama are very well trained, well done. Or no? If I wrote them up on the board, would you be able to work out what happens or no? Shama, yes, no. It's okay, doesn't matter, I just need to know. Usharika, not really. Okay, and could you tell me which electrode loses mass? Would you be able to tell me which one loses mass, yes or no? Not too much of an idea. Okay, well, we'll go through it on the board. Okay, we'll go through it on the board. I'm just coming back to the share. We'll come back to that. So the linked ideas we need to know about: reactivity of metals, the oxidation reduction, you say, you know, cation, anion, the words we will make sure, but it sounds like that is okay. The cell notation, and then the electrode potentials. So I'm going to show you some electrode potentials so you can see what they look like, because what they look like is really important. And we are looking at zinc and copper particularly. And it would be worth you writing down just the zinc and the copper details. So Zn2 plus 2 electrons goes to Zn, negative 0.76, and Cu2 plus 2 electrons goes to Cu, positive 0.34. If you just look at this table, you should see some things which are you might not notice at first, but I'm going to point them out to you. If we look at the most reactive metals in this table, they're up towards the top: potassium, sodium, calcium, magnesium. Their electrode potentials are negative numbers. If you look at the very unreactive metals down the bottom, their numbers are positive. Okay, so reactive metals have negative numbers and the unreactive ones have positive numbers. Now that's very important, and we're going to come back to that. Okay, so here we go. I'm now going to do on the board, I'm going to explain how this works. Okay, just going to change my camera and hopefully you will be able to see the board in just a minute. Okay, so they had, I'm going to draw it slightly differently. The way that most questions will have it is like this, either in beakers like this or a big beaker with tubes to collect the gas if it's given off. We have electrodes, which are normally just pieces of metal. And in the example that I just showed you, this one was copper, and it was in a solution which was copper sulfate. And in the solution of this one was zinc sulfate, so they would both be AQ. And this is zinc. Now, so far, we don't have a battery or anything like that. And what we are going to do is we are going to connect them with a voltmeter. They need something else to connect the circuit, to complete the circuit. And the thing they need is called a salt bridge. And it goes across here. It is called a salt bridge. It is a bridge which connects them via a salt. A salt bridge. So we've got the solutions, we've got the metal sticking into them. Now, if we look at the electrode potentials, they look like this. They are always written as the ion picking up electrons, okay, gaining electrons. So the Cu2+ picks up 2 electrons and turns into copper. So this is this one, and its electrode potential, which is written an E with a circle above it, and sometimes it's got a line through it, that doesn't matter, is 0.34 volts. That's positive. The Zn2+ plus 2 electrons goes to Zn, and its value is negative 0.76. What happens next is really simple. I just need another pen. What they don't show you in this, when it's written like this, in many of the questions they write it like this, but it's not really. It's actually a reversible arrow like this. And that means it could go either way. In other words, it could go this way or backwards. The gain of electrons is reduction. So the copper ions are picking up electrons and being reduced to copper. the zinc are picking up electrons and being turned into zinc. That's reduction. Now, metals, when they react, they have very few electrons in their outermost shell. Group 1, 1 electron. Group 2, 2 electrons. Group 3, 3 electrons. Non-metals gain and metals lose. So when a metal reacts, it turns into the iron. Because zinc is more reactive than copper, we would think that zinc would be more likely to go the other direction. In other words, zinc would lose electrons because it is more reactive. What is important about this is using this, and we're going to see how to use this. What is basic about this is that one of these is going to go forwards and one is going to go backwards. And the rule is this: the most positive one goes forwards and the most negative one goes backwards. The most positive one, it's worth writing down perhaps, the most positive one goes forwards and the less positive one, the more negative one, goes backwards. So the copper, Cu2 plus 2 electrons goes to Cu positive 0.34. This one is going to go in that direction. The zinc, because it is more negative, is going to go the other direction. Where's my board rubber? I've lost my board rubber. Oh well. So it's going to go in that direction. So in other words, the Cu2 plus is going to turn into Cu, and the Zn is going to turn into Zn2 plus. Now that means that the Cu is going to go from the Cu2 plus in the solution onto the rod, and the zinc is going to go from zinc into the solution. We'll just go through that on the other computer. Okay, let me go back to sharing my screen. Now let's just look at this again. So here are the numbers, okay? So with an electrode potential, and this may be worth writing down, I said it was probably worth writing down just the zinc and the copper values and the equations. And here it shows them as reversible reactions. And the thing to remember is this. Number one, the most positive of any two of them goes forwards. In other words, left to right. So whenever we look at two of these, we always compare two. The most positive one goes from left to right. That means that the less positive one goes backwards. So the less positive one is the zinc one. That is going to go from right to left. Now, to work out the voltage produced by the two, what we call half cells joined together, we change the sign of the one which goes backwards, and then we just add up the voltages. Let me do that on the other board. Let's just go through it again. The most positive one goes forwards. The less positive one goes backwards. If it goes backwards, we change the sign. So the zinc is the negative one. So it goes backwards, and that becomes positive 0.76. And so the whole voltage is now positive 0.76 plus positive 0.34, and it will be 1.1. If we go back a couple of pages to the picture, you can see here on the voltmeter, it says the voltage is 1.10 volts, which is what it should be. Look again. Here it is. The more positive one goes forward, that's the copper, goes from left to right. The zinc goes backwards. We change the zinc sign, so it becomes positive 0.76, and add them together, and it becomes 1.1. Okay. All right, so here they are. Very simple. Negative 0.76 becomes positive 0.76, and then we just add them together. Okay, all right. Okay, so we're going to go back a little bit. We're going to look at this one, and so we can say what's happening. So in copper sulfate, our copper, oops, sorry, I didn't change my camera, did I? My apologies. Okay. In copper sulfate, there are Cu2 plus ions, Cu2 plus Aq. In zinc sulfate, zinc ions, Aq. Because this one was positive 0.34 and this one was negative 0.76, this one goes picking up electrons. So in other words, the Cu2 plus will pick up electrons and turn into copper, so the electrode will get bigger. And the zinc, because it's negative, it will go the other way. It will not pick up electrons, it will drop electrons off. That means the zinc will become zinc ions. So this one, the ions pick up electrons and turn into, whoops, sorry, yes, 2 plus, turns into copper. That's what happens here. And here the zinc turns into ions and therefore loses its electrons. Okay? So in other words, overall the the copper ions will go into copper and the zinc will become zinc ions. To work out the voltage, the more positive stays positive, the more negative changes its sign, so that becomes plus, and then we just add these two together, which becomes 1.10 volts. So that's how we work it out. Okay, let's try one for you. Let's get one for you. Let's see if you can do one. Okay, this is recorded, so if you need to see it later, I will send your supervisors, I will send them a copy of the film, but I'm going to set up a different one now and see if you can do it. So I'm going to completely change the system. So I'll get rid of that. So I'm going to have a different pair of metals. Let's go for silver and silver ions and magnesium ions. Okay. Now, you know that magnesium is way more reactive than silver. Silver is really unreactive, which is why it is made into jewelry and so on. To work out what is happening here, I'm going to give you the equations. Ag plus an electron, reversible reaction, Ag, and its E naught is positive 0.8. Okay, magnesium 2 plus, it doesn't matter that it has different numbers of electrons. That doesn't change things at all. So this one here, its E naught value is negative point, I think it's negative 2.37 volts. Okay. I'm going to give you a moment. What I want you to do is to work out which one goes forward. So which one goes from the positive ions to the neutral onto the rod, and which one dissolves, and what the whole... Can you mute, please? Can you mute, please, Dandora? Thank you very much. So what I want you to do is to try to work out what happens in each one of the cells, each one of the half cells, and what the whole voltage will be. I'll give you a moment just to look at it, and try and think what happens. Hopefully you can see that okay. I know it's a little bit of reflection, but hopefully you will be able to see that. Have a think, see what's going to happen, and I will come back in just 2 minutes. Okay. Are you feeling good or not so good? Is it good or not so good? Genesis, I'm looking at my computer. Genesis, I can see you. Good. Usharika, not so good. Dandora? That's good. Okay. Glory, how's it going? Is it okay? Glory? Good. Shama? Shama, I think will be okay. Excellent. Okay. So some people not so good, some people better. Okay, remember the pattern. Pattern is really fairly simple. Okay. Guys, Dandora, could you? Dandora, please keep muted because otherwise people can't concentrate. Okay, so let's have a look at this. Can somebody tell me which one goes which way? Can anybody tell me which one goes which way? I'm going to come back to my other camera just for the moment. Okay, so what happens? Does the silver go from Ag plus to Ag or Ag to Ag plus? So we're going to really simple, okay? Does it go forward or backwards? Okay, the silver one, does it go forwards or backwards? Ag was positive 0.8. Does it go forwards or backwards? Shama Genesis is saying forwards. Usharika are holding their nerve. Perhaps not. Usharika, you have to have courage in chemistry. Glory, what do you think? Forwards or backwards? They think forwards. Dandora all think forward. Shama, what do you think? Forwards or backwards? Forwards or backwards? Shama, forwards, backwards? They think forwards. Usharika, you seem to have a little bit of a problem with this. So I'm going to explain in just a minute. So the other one was magnesium, and its value was negative 2.37. Remember what I said? The more reactive the metal, the more negative the value for the reduction potential, okay? The more reactive, the more negative. Okay, so does the magnesium go forwards or backwards from Mg2+ to Mg or Mg to Mg2+? Forwards or backwards for the Mg? What do you think, Shama? One person at least, the great spokesperson for Shama, the new president of Kenya, is going with backwards. Shama, oh, some people going forward, some people going backwards. Oh no, desperate. Glory going backwards. Genesis going forwards. Okay, let's just go back. Let's just go back. Hang on. Let's go back to this. Here. Look at this. I hope you can see this now. Do you remember we were just looking at the zinc and the copper before? And the rule was that the more positive one goes forward and the more negative one, or the less positive anyway, goes backwards. The more positive goes forward and the less positive goes backwards. So if you look at magnesium up here at negative 2.37 and silver down the bottom at positive 0.8, the silver will go forwards and the magnesium will go backwards. Okay, that's really important that you get that. It's really very straightforward. Let's look at it again on the board behind me. Here it is. I hope you can see it okay. I know it's a little bit of reflection. I'll try and get a little bit further forward. Okay. So you always have two half cells. Half cell, half cell. You look at the values, and the more positive one, even if they were both positive, the more positive one goes forwards. In other words, this will go that direction. In other words, we will get that. The more negative one, the less positive one, goes in the opposite direction. That means it goes in this direction. Now, if we look at this, this means that Mg is turning into Mg2+. So in here, in the magnesium half cell, the magnesium will be dissolving into the solution to become more Mg2+. In the silver one, it goes from silver ions, which are in here, to silver on there. So in other words, it goes this way. The total voltage, if this one goes backwards, we change the sign and then we simply add them up. So we get 7, 1, 3, 1, 7. That's the whole voltage now. So the positive one stays the same. The less positive one, change the sign and then add them up. Okay, really important that we get that. It's a really simple rule, but that's all you have to do. And this question comes up quite often. Okay, this type of question. Now, so overall, I know that Ag plus turns into Ag, and I know that Mg turns into Mg2+. How we write the cell notation is like this. We go with the left-hand side, normally, and we say, okay, Ag plus turns into Ag. Okay, I've got that right. Right-hand side, Mg turns into Mg2+. Now what happens is this. It is always set up either left to right or right to left, it doesn't matter. And we join the two solutions, the Mg2+ and the Ag+, so that it goes in a sensible direction. So I know Mg turns into Mg2+, and Ag+ goes to Ag. The salt bridge connects the Ag+ and the Mg2+. So what we write is we say we show the salt bridge often like a dotted line, and on one side will be one of the solutions, on the other side will be the other solution. Don't worry, this is quite complicated. but I'll show you it and then hopefully you will understand. So the Mg2 plus, the Mg becomes Mg2 plus, and the Ag plus becomes Ag. So I'm going to go Ag plus here becomes Ag, and Mg here becomes Mg2 plus. This way I have the two solutions next to each other, connected by the salt bridge. We draw a solid line between the Ag plus and the Ag, and the Mg and the Mg2 plus. This means a phase or physical system change, because this is solid and this is AQ. So solid AQ, different physical system states, Mg plus. And so what I've got here is now a system which follows this. It looks like it's the wrong way round, but it follows the direction that it happens, because from here, Mg does turn into Mg2 plus. The Mg2 plus is connected to, with the salt bridge.
Excuse me.
Yes? I'll come to questions in just a moment. Hang on just a minute. I'll come to questions in just a minute. And then the Ag plus turns into Ag. Okay, I'll take questions now. Ask a question. Somebody had a question. Do ask the question now. Oh, they're writing it down. Hang on. You can't see the board properly? Okay, hang on. I'll just try and make it a bit better. Hang on. Wait a moment. Is that better? No? Is that better? Better now?
Yeah, that seems better.
Okay, good.
Oh, Silver Spring are saying it's not. Somewhere you can't see it. Silver Spring.
Not visible.
There is reflection. Eh?
There is, but hang on. I will just try moving the camera and see if you can see it like this.
Dennis is mute.
Yes. Okay.
Okay, I'm sorry about the reflection, but let's go through what is happening here. So the first thing that you need to know is that we always have the two half cells. Each one of them has a reduction potential, an electropotential. The more positive one goes as reduction, the other one goes in the opposite direction. Okay, that's the basis of it. If we want to calculate the total voltage, what we have to do is to work out the more positive one stays positive, the less positive one changes its sign, then we add them together. Okay, that's all it is. It's not terribly complicated, really isn't. Okay. I'm very sorry, Ashirika, if you couldn't see the board properly, but hopefully I will be able to I will tell you what I'll do is I will write an answer out so you can see it better. Okay, I will make sure that you can see it properly. Okay, so let's go back to the PowerPoint. So here's the PowerPoint. Hopefully you can see the electrode potentials. All right, so the thing to remember, when you look at them, the more positive one goes forward, the less positive goes backwards, okay? And that means really simply that the copper is going to go from Cu2 plus to Cu, that's a reduction, and the zinc is going to reverse. It's going to go from Zn to Zn2 plus. Because it reverses, we change its voltage sign, so it becomes negative 0.76 becomes positive 0.76, and then we add them together. Okay, so if we just add them together, it just becomes 1.10, which is what it showed in the picture at the very beginning. So if we go back, here it is, there it is, 1.10. Okay, that's really simple, 1.10, because they go in those directions. The last thing that you have to be able to do is to be able to identify what is happening to electrons in the system. Okay, you have to work out what is happening to electrons in the whole process. So let's have a look at this. So the copper is going to go from Cu2 plus, use up electrons, turn into Cu. The zinc is going to turn from Zn into Zn2 plus, kicking out electrons, losing electrons. That means the electrons will go round the outside through the voltmeter to the copper. So if I go back to the picture which I had on the board behind me, which is not very clear, maybe I will write it down. I will show you a piece of paper. I'm sorry about the reflection. They are very reflective sheets. I'll just show you something on my camera in just a moment. So I'm just drawing something that you will be able to see. It's very, very simple. Hang on. My artwork is not very good, you will see. It doesn't matter. Hang on, nearly done. It's a very beautiful piece of artwork, you will agree, in just a moment. Here we are. Okay, ready? Wow, look at my art. Yeah, okay, it's rubbish. Oh, it's Shama, stop laughing. It's rude. Okay, so here is my artwork. Okay, it's very beautiful, but no reflection, see? So what is happening here is that because the copper number is more reactive, sorry, that is more positive, the Cu2 plus is turning into Cu. And because this one was more negative, the Zn is turning into Zn2 plus. Now, if the Zn turns into Zn2 plus, it loses electrons. Because it loses the electrons will build up on here and they will go round the other side and be picked up by the copper here. Wait, I'm going to draw something else. I'm going to write something else. So in the copper, this is what is happening. So the Cu2 plus picks up electrons to turn into copper. The Zn turns into Zn2 plus and leaves its electrons. The electrons go round and are picked up by the Cu2 plus. They're the same electrons. So they're going from the Zn round to the copper electrode, where the Cu2 plus ions pick up the electrons and join on. So what's happening in this half cell here is the Cu2 plus pick up electrons which have come from the zinc and turn into copper. So the copper solution here will become less and less concentrated because the Cu2 plus is going onto the rod. There is less and less Cu2 plus in the solution. That's very important. The Cu2 plus becomes more dilute. On this side, the Zn turns into Zn2 plus. So the Zn rod electrode dissolves. If it dissolves, then there will be more and more Zn2 plus ions. So the concentration on this side becomes less, and the concentration on this side becomes more. That's very important. Cu2 plus on this side becomes more concentrated, and on this side, the Zn2 plus, Cu2 plus becomes less concentrated because it is picking up electrons and turning into copper. And on this side, the Zn2 plus becomes more concentrated and the zinc rod becomes lighter and lighter. Okay, that's what we're talking about. Great artwork, yeah? Yeah. I'm going to give myself a mark for my artwork. I'm giving myself this for artwork. Yeah. Okay. Let's go back to the questions which they had right at the beginning, which showed what that was talking about. So let's go back to the sort of questions which they said we would have in the test. So here is a question from KCSE. It says the electrolysis of magnesium sulfate solution using inert electrodes. Now, inert electrodes, when we were doing about the extraction of aluminium from aluminium oxide, which came from purified bauxite, we said inert electrodes were carbon, and they're almost always carbon. So inert means unreactive in electrolysis. So in this question here, name a suitable pair of electrodes. They would be carbon. State and explain the changes on the concentration of magnesium sulfate. Well, in here, we've got water. And on Saturday, what we will do is we will look at the role of water, what happens in solutions when there is water present. Okay? In the second one, the second question, almost exactly the same thing is being asked. Name the electrodes A and B, write an equation for what is happening at the electrode and what happens to the concentration. Here is a question just like the one we have done. What I'm going to do is give you a few moments now, perhaps 5 minutes, to work with somebody else to work out what is happening. So I want to know what the overall what is happening in each cell. This one is negative 0.13. This is negative 0.76. Remember, the more positive goes left to right and the less positive goes the other way. And then tell me what the overall voltage is for the cell. So you've got a few moments now to try and work out what is happening here. This is lead and magnesium cells put together. So try to work out what is happening in this one. Because I think at the beginning of the lesson, most of you wouldn't have been able to do this. And I think some of you may be able to now, but share your ideas with somebody else. Have a go. Not 0.45. No. Remember, the more positive one goes in its direction, and the less positive one is reversed and change its sign. Okay, so the more positive one we keep as it is. Glory? Glory? The more positive one stays the same, and the more negative one is reversed. Okay, so we change the sign of the more negative one. So which one is more negative? That's the magnesium, isn't it? Well done. Silver Spring, well done, whoever that is. Well done, that's very good.
Samuel.
Just for a change, Sam is in charge. Well done, Shama, very good. Who is that at Shama, please?
Emily.
Emily. Well done, Emily. Professor Emily and Professor Samuel, you are top of the class today. Come on, Genesis, what do we got? We're looking for a number. If you get the number, then you have got the right idea. If you can get the number, you know what is happening, which is brilliant. Dandora, I haven't had an answer from you yet. Come on, Genesis. I want everybody to be able to get the right answer, please. Come on, Wamuini. Glory, have you had another go? Down a bit, please. PB2, which one? Well, one of them goes left to right and one of them goes right to left. Usharika. The one which is more positive goes from left to right, and the one which is more negative goes right to left. Okay. So the more positive will be reduced as it's written, pick up the electrons, be reduced. And the more negative one, the more negative or less positive will reverse. Show me again, Genesis, please. Sorry, I missed that. Show me again. Yes, oh, hang on. No, not quite. No, sorry, it's the wrong way around. You've got the right number, but you've got the wrong equation. Dandora, sorry, show me again, Dandora, please. Okay, let's just have a look at it. Let's just have a look at it. Let's just have a look. It's quite important. Hang on. Okay. Let's see if we can just see enough from the other camera without too much. Let's see if I can get this up a bit. Hang on. Just a moment. Let's see if that will make it. I know it's a funny angle, but can you see that okay? This says Pb2 plus, let me just switch on the light, see if that, is that any better? Just about. I'm sorry about this. We'll get it better. We'll get it better for next time. Pb2 plus, 2 electrons, Pb, -13. Mg2 plus, 2 electrons, Mg, -0.76. The most positive one goes forwards. This one is more positive. So this one goes in that direction. This one, the magnesium one, goes backwards. When it goes backwards, we change the sign of that one, the more negative one. If I add these up now, I get the answer 0.63. So the overall change is that Mg goes to Mg2 plus and Pb2 plus goes to Pb, and therefore the equation will be Mg plus Pb2 plus goes to Mg2 plus and Pb. Sorry about the reflection. I will make sure that next time we don't have reflection. I will, it's a very odd day here today, I'm sorry. So, in that question.
Excuse.
Yes, Samuel?
Excuse. What about when you are asked to write a salt bridge equation?
Okay, I'll show you it in just a moment. So in this one here, if we were going to write a salt bridge equation, remember that the two solutions have to meet in the middle. So the Mg2 plus and the Pb2 plus will meet in the middle. Because the Pb2 plus turns into lead, the Pb2 plus will be on the right-hand side because it goes left to right. So I'll show you it. On my wonderful artwork. It will look like this. Because the magnesium, the two solutions have to be with the salt bridge in between them. Because Mg turns into Mg2 plus, it has to go this way. And the lead, the Pb2 plus, turns into Pb. So it has to go that way, okay? So in general, the easiest way to think about it is to look, and the one which is reduced, the one which actually reduces, the one which has the more positive value should be on the right-hand side, okay? And it should go from the solution to the metal, from the solution to the metal. And the one which is oxidized, in other words, goes backwards, goes from the metal to the solution. So solid line meaning change in physical state, Mg, solid line Mg2 plus, either 1 or 2 dotted lines for the salt bridge, Pb2 plus, change of physical state, lead. Okay, that's how the salt bridge would look. And the electrons will go, because the Mg turns into Mg2 plus, the electrons will go from here to there. They will always go from the one which is oxidized, because that's losing electrons, to the one which is reduced. Right, on Saturday, if you want to come on Saturday, from 11 till 12, and I will record it like I have this one. So if you can't come, that's fine. I will record it and we will make sure that you can get at it. We will look at more questions to do with this particular part of the specification of the syllabus. And then next week, we will do moles. We will do some moles questions because we had some people asking for moles calculations. We have about 3 weeks left, this and 2 more weeks after this. So I would like to know what other topics people would like to study. But next week, on Saturday, we will do electrolysis. Next week, we will do moles. And then there will be either 1 or 2 more sessions after that. So if you have an idea of something you would like to study, then tell me.